Okay, in the name of God, Mr. Ghassan, do you have my voice? Mr. Ghassan Al-Hasnawi, do you have my voice? Mr. Ghassan Al-Hasnawi, do you have my voice? Welcome, Muhammad. Okay. وعليكم السلام. أهلا وسهلا. In the previous session, we say that L1 can be considered as an element of M of G, okay? Group algebra can be considered as a subset of major algebra. This is group algebra, this is major algebra. And we know that for any two elements of M of G, we have mu star nu, the convolution product of mu and nu by this definition. So for any mu in M of G and for any f in L1 of G, we can define mu star f instead of mu star nu. We can define mu star f because we can consider this element of L1 of G as an element of M of G, so that we have a multiplication in M of G, mu star f. And so we have this definition. For any mu in M of G and for any f in L1 of G, we define mu star f equal to mu star mu f. We see the definition of mu f as a functional on C0 of G, so that mu f is an element of the dual of C0 of G, and by the representation theorem this dual equal to M of G, so that these two are two elements of M of G, and we have the definition of convolution product in two measures. Now we can see that for any h in C0 of G, by this definition, we have mu star mu f of h equal to this integral for any h in C0 of G. The double integral h of xy d mu f d mu f. And by the Fuhrman's theorem we can replace the order of these two integrals, so that this is equal to integral of h of xy d mu f d mu, and this is equal to this, because this integral equal to this by star prime, we see this star prime, this equality, integral of h d mu f equal to integral of f h dm. Okay, this is our hard measure. So that the integral of h d mu f equal to integral of h multiplied by f d mg of y, and this is equal to this integral because mg, this measure is a regular Borel measure, and so this is left invariant. This is left invariant. Okay, so the integral of any function such as h, zy, d mg of y equal to the integral of h y d m y mg of y. Okay, we can omit this z. Now our function in this equality is this function. Okay, for example, h of y equal to h of xy and f of y. If we consider this function, we can add it any function such as z or x inverse in the left side of this function, and this multiplication equal to identity, so that this is h of y, this is f of x inverse y, d mg of y, and then d mu x. Okay, this property is very important in hard measures, because hard measures are left invariant. This integral for any z, okay, for any z in G, these two are the same, and in this line we consider z equal to the inverse of x for this function. Okay, please note that this x is a constant. This is a constant, so that this is a function dependence on y. This is a function by y variable. Okay, so this is equal to this integral, and by the Fubini's theorem again we can replace the order of these two integrals, and so this is equal to this integral. Now we denoted h1 of y equal to the integral of f of x inverse y d mu y. By this notation, for any h in C0, we see that mu h1 of h equal to the integral of h d mu h1, and by star prime again, this integral equal to the integral of h multiplied by h1 dmg. And if we replace h1 by this definition, we see that this equal to this integral. If we compare this by this, we see that these two are the same. Okay, so that mu star f of y equal to this integral. Because for any h in C0, we see these two are the same. Therefore, these two are equal. Mu star mu f equal to mu of h1 or for any y in G, these two are the same, and this equal to this, so that mu star f of y equal to this integral. And we prove this an applicable equalities. Okay, in your book okay, let me review this in the next. Let me complete this. So we define mu star f, mu star mu f, and we see that mu star mu f of any h equal to this, and also mu h1 of h equal to this again. Okay, so that for any h, mu star mu f of h equal to mu h1 of h, so that these two functions must be equal. These two functions must be equal. And so mu star f must be equal to this integral. Now let G be a locally compact group. We define some subsets of L infinity. CB of G equal to the set of all f from G to C functions from our group to the complex numbers such that f is continuous and bounded. C is the first of continuous and B for bounded. CB of G, the set of all f from G to C such that f is continuous and bounded. CB of G is a subset of an infinity of G. And CB of G is invariant subspace of L infinity. On the other hand, if f be in CB of G, then for any G in G, this translation, left translation of f and right translation of f are in CB of G again. Okay? And for any mu in M of G and for any phi in L infinity, we define mu star phi of G equal to this integral, the integral of phi of H inverse G d mu, okay? So if G1 be an element of G, then delta G1 star phi of G equal to the integral of phi of H inverse G d delta G1 of H, so that this is equal to phi of G1 inverse G or LG1 of phi of Y. Therefore, we prove that these two are the same, delta G1 star phi and left translation of phi in G1 for any G1 in G and for any phi in L infinity, these two are the same. Similarly, phi star delta G1 equal to RG1 of phi. Okay? Now, let me introduce another book for you. We work in the rest of this course on this book, lectures on amenability written by Walker Ronde. This is a very important book in amenability that contains these chapters. This is an elementary chapter we study this chapter amenable locally compact group. Okay, but for this we need some preliminaries that such as these elementary facts expressed in the appendix A. Okay, so we begin from appendix A. Okay, this is chapter 1, amenable locally compact groups. Okay, for this we see the appendix A. Let me begin from this appendix. This appendix is familiar for you. Abstract harmonic analysis. Okay, a locally compact topological group is a group G which is also a locally compact host of a space such that these two maps are continuous, and you know this definition. Binary operation and the inverse function must be continuous in topological groups. Okay, let G be a locally compact group. We write M of G for the space of all finite complex regular Borel measure on G. That I define this space completely for you. This is measure algebra. By Ree's representation theorem, M of G can be identified with the dual space of C0 of G. We want to make M of G into a Banach algebra. By this, a star or convolution as a binary operation on M of G. Definition: let G be a locally compact group and mu are in M of G. Mu and mu be in M of G. The convolution product mu star nu is defined by this equality, mu star nu of f equal to this integral, and you see this definition too. By Fubini's theorem, the order of integration in this equality is irrelevant. Okay, it is routine to check that M of G and A star is a unital Banach algebra, that we see this in the previous sessions. The measure algebra of G is this algebra, which is commutative if and only if G is abelian group. What is the identity element of M of G? We see delta E is the identity element of M of G. Okay. Dear students, do you have my voice? Okay. Welcome, Sajjad. we have some exercises. Please write these two exercises for me. Exercise A11, A12. As your homework. Let me write for you. يرجي هل هذين التمرينين وإرسالهما إلي. Okay. And we have this definition for Dirac measure. For any G in G, the point mass delta G, or the Dirac measure at G, is defined by this equality, delta G of F equal to F of G for any F in C0 of G. We use Rees representation theorem again, okay? Because this measure can be considered as n functional on C0 of G. So we define the act of this on any element in C0 of G. And a measure in M of G is called discrete if it is in the closed linear span of this, and we see these definitions too. Okay. And we have this important theorem. Let G be a locally compact group. Then there is a non-zero regular positive Borel measure such as Mg on G. This measure is called left hard measure on G, which is left invariant by this definition. Mg of Ge equal to Mg of E for all G in E and for all Borel subset E of G. So we have a regular left invariant measure on all locally compact groups, and this measure is unique until constant. On the other hand, or in the other word, if Mg prime is another non-zero regular left invariant Borel measure on G, then there is a constant C such that M prime equal to this scalar multiplication of M of G. These two differ only in a constant C. Okay. Example, on our n hard measure, it is n dimensional Lebesgue measure And if G is discrete, counting measure is Hall measure. Counting measure is Hall measure. Please note that it is very trivial that counting measure is left invariant, because we know that let G be a discrete group and mu be the counting measure on G. Then mu is a left invariant measure, because you know that for any subset of G, mu of E equal to the number of element in E, if E is finite. If E is finite, is the number element of E, and in the otherwise is if E is infinite, this is equal to infinity. Now, if E be a subset of G arbitrarily, and G be any element of G, we have two cases. One, E is finite. Two, E is infinite. In this case, we see that mu of GE equal to the number element of GE, and this is equal to the number element of E, and this is equal to mu of E, so that these two are the same. And in this case, mu of GE equal to infinity, and this is equal to mu of E. And these two is trivial, because if we write a star because, for example, if E equal to A1 AN, then GE equal to GA1 GAN. And the element of this set are different because if, for example, GAI equal to GAJ, you can multiply G inverse in the both side of this equality. G inverse GAI equal to G inverse GAJ, and this shows that AI must be equal to AJ, so that if we consider distinct elements in E, these are distinct, and the number of this set equal to the number element of this set, so that these two are the same. But this is the measure of GE and this is the measure of E, so that these two must be equal. And if E is an infinite set, then GE is infinite too. So both of these have infinite measure, so that in each cases mu of GE equal to mu of E. So in discrete spaces, please note that if G be a discrete group, G is discrete, okay, then beta of G equal to whole of the power set of G. Any subset of G is a Borel set, okay? So that we check this equality for any subset of G. For any subset of G. Please note that a Borel measure is left invariant if we have this equality for our Borel subset. But in our example, any subset of G is a Borel, so we prove this for any subset of G in this example, okay? In this example. And also we have this exercise that G be a non-discrete locally compact group. Show that Mg of G is 0 for G. Conclude that the homomorphism A2 is an isomorphism if and only if G is discrete. So, okay, this is trivial, and we have this definition that we see the definition of convolution of two integrable functions. Let G be a locally compact group and F1 and F2 be two elements of L1 of G. Their convolution product F1 star F2 is defined by this equality F1 star F2 of any G equal to this integral of F1 of H, F2 of H inverse G, D and G of H. Okay. Please solve this exercise 2 because this is very important. For any two elements in L1 such as F1 and F2, F1 star F2 belong to L1 again. Okay. As in the case of the major algebra, it is routinely so somewhat tediously check that L1 and A star is a Banach algebra. Does that deter you from actually checking it? If G is discrete, L1 equal to this little L1, so that L1 is a unital. Okay. In this case, you know that L1 is not unital in general. M of G is a unital Banach algebra, but L1 is not unital in general. But in discrete case, L1 is a unital Banach algebra. Okay. Let G be a locally compact group and U be a basis of neighborhood of A of G, identity element of G, and EU be a net in L1 with the following properties. EU be positive for any U, support of EU be a subset of U for all U, and the L1 norm of U equal to 1 for any U in U. Then this is the bounded approximate identity for L1, so that we have this important theorem. L1 of G always have a bounded approximate identity. Bounded approximate identity. Let G be local compact group, then L1 has a bounded approximate identity. Always we have this. I think you see the definition of bounded approximate identity. Okay. Yes, I write the definition of bounded approximate identity for you. So in this corollary we see that For any locally compact group, G L1 of G has a bounded approximate identity. And also for any locally compact group, there exists a unique continuous function such as delta from G to 0 infinity. The value of this function is non-negative or positive. This function is called the modular function of G. And this function have these properties: delta G of GH equal to delta G of G multiplied by delta G of H for any G and H in G, and mg of EG equal to delta G of G multiplied by mg of E, because mg is left invariant, not right invariant. Okay, mg of GE equal to mg of E, but mg of EG by right multiplication equal to this for any G in G and for each Borel subset E of G. Okay. And if delta G equal to 1, the group G is called unimodular. Trivially, abelian and discrete group are unimodular, but so are all compact groups are unimodular. In this case, theorem A110 implies that delta G is a compact, delta G of G is a compact subgroup of this, because we know that any continuous function maps compact set to compact set. If G be compact, since this is continuous function, delta G of G must be compact too. Okay. And I write this map for 2. L1 can be embedded in M of G. We see this embedding. Let G be a locally compact group. Then the set of all measures in M of G which are absolutely continuous with respect to M of G is closed ideal of M of G, and this is isometrically isomorphic to L1 of G as a Banach algebra, and we see this theorem in the previous session. Okay. And we have this proposition: for any locally compact group and for any mu in M of G and for any f in L1, we have these two equalities. We see this equality in this session. Okay, we see this equality mu star f of y equal to this. Please prove another equality as an excessor. Okay, so please prove this as an excessor. Let me write this for you. يرجى الحصول على غرة أخرى كممارسة. It is similar to the proof of this, okay? Completely similar. And we have these two definitions that I write this for you. Remark, it can be shown that mu star phi and phi star mu as defined in these equalities are well defined and satisfies these inequalities. Okay. Now we have these sections. Invariant subspaces of L infinity. Let G be a locally compact group. In definition 113, we define what we mean by a left invariant subspace of L infinity. This is the definition of invariant subspace. A subset E of L infinity is called invariant whenever for any F in E and for any G in G, LG of F and RF of F belong to E. Okay. This is the definition. One. We see this definition in chapter 1. Okay. E is called left invariant if delta G star phi belong to E for any phi in E and for any G in G. And we know that delta G star phi equal to the left translation of phi. Okay. Please note that we prove this for you. We prove this equality. Delta G star phi equal to the left translation this equal to delta G star F. Delta G star F. So a subset E of L infinity is called invariant whenever for any F in E and for any G in G we have this. So as an equivalent definition you can write for any f in E and for any G in G, delta G star phi belong to, because delta G star phi equal to this left translation. Delta G star F belong to E. If we have this or this, then this E is left invariant. And if for any G or G of F belong to E, we say that E is right invariant. And if E is left invariant and also right invariant, we say that E is an invariant subspace of L infinity. Example, L infinity itself, whole of L infinity, and CB of G are invariant subspace of L infinity. And for any f in CB of G, we can write the subnorm, because this supremum is finite. If f is bounded, this set is bounded, so that the supremum must be finite. The supremum is a real number, and we can define this norm. Okay. So in this section, we study the invariant subspaces of L infinity. And this is the definition of invariant subspace. This is very important. For any f in E and for any G in G, delta G star F belong to E. And I say that these two definitions can be separated. Let E be a subset of L infinity. Okay? E is called left invariant, if and only if for any f in E and for any G in G, Lg of f belong to E, or equivalently for any f in E and for any G in G, delta G star f belong to E, and E is called right invariant if and only if for any f in E and for any G in G, RG F belonging to E, and this is equal to for any F in E and for any G in G, F star delta G belonging to E. Okay, these two are equal, and finally E is called invariant if and only if E is left and right invariant. Okay, dear students, do you have any question? Thank you very much. Thank you very much. We continue in the next session, inshallah. Thank you for your attention and goodbye.